This lecture covers implicit differentiation as opposed to explicit. In explicit differentiation, which we have been doing, you can get y or f of x all by itself on one side of the equation prior to differentiating. With implicit, you can't. So the procedure is, first of all, to differentiate with respect to a variable, and usually it's dy dx, dy dt, something like that. So with respect to x or t, be sure to include chain rule derivatives, as we'll see when we look at some examples. That's all the calculus in this problem. Then after that, it's a lot of algebra. You get all the derivative terms on one side of the equation and factor out the derivative while putting all the other terms on the other side of the equation. And then you simply divide to get the derivative by itself because you are trying to solve for the derivative. Simplify using the original equation occasionally happens with second derivatives. If you're actually solving for an actual value of the derivative, you can plug in after step 1 doing the differentiation and before the algebra, and then do the algebra after you plug in numbers. You have more numbers and less letters when you're doing algebra, if you prefer that. So on to some examples to make this a little more concrete. Okay, this is not a function that can be easily solved for y, and so we're going to differentiate it implicitly. So first of all, working your way from the outside in, you do the derivative of sine, which is cosine. And so we have cosine x squared y. Then we've got to do the derivative of x squared y, which is going to be product rule. So we'll have derivative of x squared, which is 2x, times y, plus x squared times the derivative of y, which is y prime. So you have to make sure you include the y prime, minus, then the derivative of tangent is secant squared, so secant squared 3y, times the derivative of 3y, which is 3y prime. You could also put dy dx if you prefer instead of y primes, and then equals derivative of x, which is 1. So that's all the calculus. So now what we'll do is distribute cosine x squared y, put these together to get this long expression here. And meanwhile, what I also did was when I distributed cosine x squared y with 2xy, I subtracted to the other side. So I've got this piece is over here, and this piece I kept on the left also because it has a y prime, and the parts without y prime I put on the right. So now, left side, factor out y prime. So go y prime times this minus this. And then finally, if you want to get y prime all by itself, you simply divide the right side by all of this, and so this would be your derivative, or y prime, or dy dx. Okay. Let's see, sine to the 1/3 x cubed y minus the 4th root of 5y squared equals some constant c. All right, a lot going on here. So first I'm going to write these things, putting exponents in the correct place so we make sure we get the order right of all the chain rule issues that we have in this problem. All right, so first thing is power rule. So that's here. Then working your way in, then you've got derivative of sine, which is cosine. Then working your way in, you've got x cubed y, which is going to be product rule. So derivative of x cubed is 3x squared times y, plus x cubed times the derivative of y, which is y prime, minus, then we do power rule there. So 1/4 5y squared to the negative 3/4, and the derivative of 5y squared, which is 10y, and then derivative of y squared, y prime, equals the derivative of constant, which is 0. So that's all the calculus. Notice we don't bother putting x primes when we do these things because x prime, derivative of x with respect to x is just 1. So now we multiply some things out over here. The idea being to get everything with y prime well, I got everything on the left side of the equation. So what I've done here is I've distributed these pieces with these two. That's why it's taking up much more space. So now I note the terms that have a y prime. So that's this term here and this term over here. And we leave those on the left, factoring out y prime. This term over here does not have a y prime, and so I subtract it to the other side. And then lastly, you divide all of this junk by all of this junk, and there's your derivative. So algebra is a big part of the problem once you get through this differentiation. Okay, some exercises. X squared minus y squared equals 16. Derivative of x squared is 2x. Derivative of y squared is 2y times y prime. Derivative of 16 is 0. And then you just get the y prime stuff on one side, the non-y prime stuff on the other. Divide both sides by 2y. First I divided both sides by 2, divided by y, so y prime is x over y. Okay, x cubed minus xy plus y squared equals 4. Okay, derivative of x cubed, 3x squared, and then minus, and then xy is going to be product rule. So I have x times the derivative of y, and instead of writing y prime this time I put dy dx. You'll see it both ways. And then plus derivative of x, which is 1 times y. Yeah, so dx. I just wrote that in this time to make it clear that it is 1, but if you want to, if you're wondering why didn't we do it before with dx? Well, it's because it's just 1. Derivative of y squared is 2y times derivative of y with respect to x, so dy dx. Derivative of 4 is 0. So we get all the dy dx stuff together. Well, first we distribute this negative, so I get all the dy dx stuff on one side and factor it out, and I put all the non-dy dx stuff, the 3x squared minus y, on the other side. So it becomes y minus 3x squared, and then finally I divide to get this as my derivative. Okay, this is going to require product rule again. So we have derivative of x cubed times y cubed plus x cubed times the derivative of y cubed, which is 3y squared times y prime, minus the derivative of y, which is y prime, equals the derivative of x, which is 1. So all the y prime stuff we leave on the left, all this non-y prime stuff we put on the right. We factor out y prime from the stuff that has a y prime in it, and then you divide again. So here's your answer. Okay, some more trig. Derivative of sine x is cosine x, and then plus 2 is a constant multiple. Derivative of cosine is negative sine. Derivative of 2y is 2y prime. Derivative of 1 is 0. So get all the y prime stuff on the left, get all the non-y prime stuff on the right, and then again we just simply divide and get rid of some negatives. Okay, this time we want to find the derivative and find the value of it at a specific point 8, 1 on the curve. So find the derivative, and here we've got our y prime again, or dy dx. The derivative of 5 is 0. So I divided off 2/3 from both sides, and I have this expression. And then I could have solved for dy dx and then plug in the numbers, but I chose to plug the numbers in now. So I plug the numbers in for x and y. Get it down to here because 1 to the negative 1/3 is just 1, 8 to the negative 1/3 is a half, and so dy dx therefore is negative a half. So on this curve, at this point, the slope of the tangent line is negative 1/2. Okay, tan x plus y equals x, and what's the slope at 0, 0? Incidentally, if you only knew that y was 0, you could get the x value from that, because if you plug y equals 0 in here, you'd have tan x equals x, which is only true when x is 0. So if they didn't give you the x value, you could still figure it out just from knowing that y is 0. So derivative of tangent, secant squared, derivative of x plus y is 1 plus dy dx, because the derivative of x is 1, derivative of y dy dx, derivative of x is 1. And then we plug in 0 for x and y. So secant squared of 0, 1 plus dy dx equals 1. Secant of 0 is 1, so this just goes away. 1 times this doesn't change anything, and so dy dx therefore is 0. Okay, a few more. This is now looking at the slope on an ellipse. If you take a general ellipse, which is x minus h squared over a squared plus y minus k squared over b squared equals 1, we have a center at h comma k. We have these 2 points, h plus a comma k, h minus a comma k. We go up an amount b, so that's h comma k plus b, down b, h comma k minus b. If we want to find the slope anywhere on here, realizing that a, b, h, and k are all constants. So given that, we have 2x times x minus h over a squared plus 2 times y minus k times y prime, because you've got to take the derivative of y minus k, over b squared. Derivative of 1 is 0. So we leave the y prime stuff on the left and divide off of 2, put the non-y prime stuff on the right. See, it's negative because I moved it to the right. And when I divide by y minus k over b squared, I get this as my expression for the slope, which makes sense because if x was equal to h, then I would be here or here, and I've got flat tangent lines. And if I put in h, I'd get 0. And if y was equal to k, I'd be here or here, and I have vertical tangent lines. And if y was k, I'd be divided by 0, so I'd have a vertical, I have no slope, so it'd be a vertical line. A few more problems with second derivative now. So as far as second derivative, you just differentiate twice and plug in what you have for the first derivative. So x squared plus xy equals 5. Okay. So incidentally, you could do this explicitly, which is always better if you have a choice. You could change this equation with a couple algebraic transformations into this. But if we're just doing it implicitly, this is 2x, xy. This will be product rule, so x times the derivative of y plus y times the derivative of x, which is 1. Derivative of 5 is 0. We get the non-y prime stuff on the right and divide by x. So now if I divide everything by x, I have this. Now if I want to get the second derivative, I've got to take another derivative here. So derivative of negative 2 is 0. So I'm really just doing the derivative of negative y over x. So it's quotient rule, square the bottom, write it up top, and then times the derivative of the top minus the top times the derivative of the bottom. Now I've got a y prime, so I've got to find an expression for that. Well, here's y prime, so I have to plug this expression in here for y prime. So I've got all of this. The x's will cancel, and I eventually get to here. Now, something to realize, if I had used it this way, then I could immediately differentiate to get over to here, and then differentiate again to get 10 times x to the negative 3. So apparently 10x to the negative 3 is equal to all of this, or 10 over x cubed, which you could show if you use a substitution. If you go back to the original equation and find one of these ways to substitute in here, you could show they're the same. Okay, second derivative for this one. So here's the first derivative, 2x minus 2y power rule, and then chain rule y prime derivative 16, 0. Solving for y prime, we get x over y, and then take another derivative. This is quotient rule, so the bottom squared, bottom times the derivative of the top, the derivative of x is 1, minus the top times the derivative of the bottom. And then I put in y prime as x over y, so I plug that in. So then the top, I get a common denominator of y, so that's why this y becomes a y squared over y. These y's can go down below as a y cubed, and I've got y squared minus x squared. However, looking back at the original equation, note that if x squared minus y squared is 16, then y squared minus x squared is going to be negative 16, so you could simplify it in that manner. Okay, last one, y squared equals 4x. So I've got 2y dy dx equals 4. Divide both sides by 2y, and so I end up getting that dy dx is 2 times y to the negative 1. So now I've got to differentiate again. So second derivative is negative 2y to the negative 2 times the derivative of y, which is dy dx. So here's dy dx is 2 times y to the negative 1. Plug it in here. So substitute it in, and you get then negative 4y to the negative 3, or negative 4 over y cubed. And so I've got negative 4 over y cubed, but you could rewrite this in this manner here. I guess realizing that that because if y squared is 4x, then 4 is y squared over x. So instead of a 4, I put a y squared over x, and then some y's cancel. So this is not necessarily better or worse than this. It's just another way to get an equivalent answer.